Welcome everyone to this presentation entitled Ensemble Modeling, Music to Your Bottom Line. My name is Gary Robinson and I'll be your host for the next 45 minutes as I explain what ensemble modeling is, why you should consider it, and show you a simple way to do it. This will not be a very technical presentation and is intended for marketers and analysts of all levels. I'm the Chief Operating Officer at Lityx. We license a cloud-based advanced analytics platform, which I'll be using today in my demonstration, and we also provide analytic consultation. I have over 20 years experience working with businesses across industries, leveraging advanced analytics to help them grow by improving performance and reducing costs. I've held senior positions at Merkle as well as Bank of America, and I have a master's degree in statistics. I'm glad your curiosity in this topic has brought us together today, and I appreciate you taking this time out of your busy schedule. I'll do my best to make sure it is time well spent. So let's talk ensemble modeling and begin with an example you may have heard of, the Netflix prize. This was a $1 million prize given to the individual or team that could improve Netflix movie recommendation algorithm by 10% or more. And the $1 million prize ended up going to only one team, as we can see here in the photograph, although there were actually two teams that qualified for it. There were hundreds of teams that participated, actually over 1,000, and it took roughly about 3 years for the 10% challenge to be realized. There's an amazing sort of little side story about this, and you can see it if you can see that table, that the two teams that both number 1 and 2 actually ended up in roughly the same place, a 10.06% improvement. But there's also, if you look at the time, a 20-minute difference. And so Belcour's pragmatic chaos ended up winning over the ensemble. And the reason I chose this is because both teams and a number of other teams used ensemble modeling to make this type of improvement. Now, their approach was much more complex than what we're going to talk about today. But it really shined the light on the power of ensemble modeling. Certainly brought it to my attention a while back, and I've always thought it was a very interesting idea. And so wanted to do this webinar and share with you, like I said, a much simpler approach that you might be able to benefit from. All right, so let's take a look then at a little bit of background on modeling, very basic, but I think it will help us as we talk more about ensemble modeling. We all recall the equation for a straight line, very boring, kind of this y equals mx plus b, but as we'll see in a moment, this will just make it especially clear when we talk about what we're doing with ensemble modeling. So in this very simplified example, you can see that y is what we want to predict, and let's say it's weight, and m is some influence on x, where x is a predictor. So let's say the predictor is age, and we believe as age increases, weight increases, and then we have some constant, b, sometimes called an intercept. And so over this short range that I show here, maybe it's not too bad a little equation or sort of a line of predicting weight from age. Certainly it wouldn't hold up as the two aren't linear throughout age. But just kind of keep that in mind, that y equals mx plus b, and we'll come back to that in just a moment. There are a wide variety of appropriate approaches and techniques that can be used when you build a predictive model, but generally they produce similarly effective results. So the majority of modelers will use a well-known or preferred technique for most business problems, but other techniques might get used as well, depending on the modeler's experience and personal preference. For example, logistic regression is a technique commonly used to solve business problems that can be viewed in a sort of binary fashion, things such as yes, no, sort of click, no click, churn, yes, no, buy product A versus B, etc. But other techniques can solve these types of problems just as effectively. So most notably, decision trees such as CART or CHADE. There's neural networks, machine learning algorithms like SVM, and there's a lot of algorithms out there. And most people don't know that many, and don't need to, because as I said, most of them typically get to a similarly acceptable answer. But what is interesting is that while these different techniques produce similarly effective results, they go about their jobs in very different ways. In some situations, one technique may be more appropriate than another, but often you can use any one of a handful. And so on their own, each technique provides the business a lift that may drive thousands or millions of dollars in performance. And so the question becomes, so why do you have to choose only one technique? Why can't we, kind of like the Netflix challenge, choose multiple techniques and combine them in some way? Kind of this notion that, together we're better. How can we take the insights from each of the techniques and combine them to perhaps produce a result that is better than any one of the techniques? And that's really what ensemble modeling is, and what we're going to talk about today. So if we were to define ensemble modeling, the definition of ensemble makes it quite clear: a collection of parts that contribute to a single effect. Therefore, you could view ensemble modeling as multiple models being used together to outperform any single one of the contributing models. And so we'll look at an example, like a response type situation, and we'll build a shade or decision tree model on some data, and then also build a logistic regression model on that same data. So two different approaches to the same objective. And then we'll also look at how we might combine these two options together. And so as I show in this little simple equation, back to that of the line, we're going to try to predict response rate, but we'll combine the logistic model score with the shade model score. Those scores will become our new model. So it's kind of like a two-stage approach. Stage one is build your base model. Stage two is build a second model that uses the scores, the predictions from the stage one for your final model. Sometimes this produces better results, sometimes it doesn't. It's my sort of point here with this is it can be done simply enough that it's worth exploring. And with all the algorithms out there now, it's also, I think, to your benefit to try multiple algorithms. And assuming, of course, that, as we said, they're appropriate to see which might perform better for you. All right, let's go straight over to our demo. So I'm going to be using, as I said, Lityx IQ. And let me pop over there. All right. So I'm going to log into a secure server, and let's see, just as all right. So this is our sort of dashboard desktop for Lityx IQ, and obviously you're not going to be familiar with this software, but it's very straightforward and simple to use. And I'll show you a few elements to it as we go along. But you can certainly take anything I'm showing you and apply it to the software you're using, or if you're not a modeler yourself, to those who are doing the modeling. Very simple approach that they'll be able to use with whatever tool they're using. This tool does make it rather simple, but they may have another means. So in this example, I'm in this project. I'm in Data Manager in this project called Ensemble Model. And I've got a raw data set that we're going to be building the model off of. And so this is 57,580 records with 739 attributes on these records. So let's just go ahead and take a look at this. So I'm going to go to summary statistics on these. And we've got a lot of variables with names that are meaningless. These would be the overlay data that's on here. And we could scroll through and look at the mean, max, min and null values, et cetera, for these unique values. I'm going to go to the last set of records and scroll down here. And we can see, in addition to all these overlay attributes, we have some other things that we could model on, like amount or cost. We're going to model on this response variable. And so this is a binary variable. It's got a value, a min value of 0 and a max value of 1. And its average is 0.1328. So 13% response rate across this data set. And this could be, in this example, perhaps an oversampled data set where we've intentionally bred in sort of more responders than non-responders, and or could just be the natural response rate. We also have a variable called test n. This just happens to be like a sequence number that is a unique identifier for each of the 57,580 records, which you can see there. All right. So let me get out of this. So this is our data set that we've read in and is now available to us if we wanted to do any kind of exploratory data analysis and look at some relationships and things like that. We've got a number of means to do so. But in this case, we'll jump straight to the modeling, kind of skipping the EDA step. We're going to go into Predict IQ. And as I said, we may start off by saying, well, we want to build a decision tree model, like a shade model. And we can do that in Lityx IQ quite simply by create new model and choosing the type of model we want. In this case, we're building response models. So when I click on Build Response Model, it will bring up this set of options. And these have already been I've already built this model, so I've already chosen the data set, and this is the only information you really need to fill out. So we're going to choose the data set, which is the base model data that we just looked at from the data that we've got available to us. We're going to choose the response field. It will only show us the fields that are binary in value, since this is the type of model we're building, response model. We're going to build it off of the ones. And the predictor variables, we'll go ahead and just select all and have it examine all of the predictors, and we don't have any force predictors in this. We don't need to fill out the rest of these unless we want to change anything about them. So we'll just leave these. The sampling is 50,000. The validation we do is the standard best practice around a data set of this size, building it on 70% and validating on 30%. We do have other options that we could choose if we wanted to. And the algorithm that we said we wanted to do was shade. And so that was selected from our drop-down box. And this is where, as we'll see in a moment, our ability to do the ensemble modeling comes in, because there's a lot of algorithms. And this is all using R as its foundation. And so we could fairly easily add more algorithms if we wanted. So we can run a model on just shade. Don't really need to do any segmenting or filtering here and adjusting these. So we'll end this. And all we have to do then is execute this model. So execute it now. Now this has previously run, would run quite quickly, but we'll just jump to the performance of this one then. And so we can see with this model, if we go to like performance details, this is the shade model. We get a lift here. We got the gains chart, and we can see kind of the percent of responders that we're getting to the percent of the file that we have. So we've got some lift. We can go ahead and look at, in this case, it was a decision tree. So we can go and look at and understand some of the predictors. So it looks like we had some summarized data at the Z+4 level that came in. One thing that Lityx IQ does is, and it can be turned on or off, is it likes to bin. It defaults to binning the categorical data as well as binning the numeric data, helping first sort of identify nonlinear relationships. So we can go through and look at this and understand what's going on. We have another view of, I'll go back to the performance summary, and we'll look at some of the lifts of this shade model quickly. So I'm just going to, there's a number of performance metrics that we can look at. So I'm just going to look at the lift ones, take off that one. That's kind of the ROC lift to throw out the scale a little. And we can see decile 1 versus 2, about a 15% lift, 1.15 Not bad. About a 2.2x increase in 1 versus 10. 1 over random, about a 53% lift over random in this example. So that, let's say this is our shade model. I mean, we don't know right now until we run some other algorithms, sort of its relative merits. So we'll go ahead and close that. And then we can separately run a logistic model. So we would do the same thing, create new model, select response, and within that, fill out everything just as we had before. Just point to the data set of interest, the field that you're going to be modeling off of. This time under algorithms and settings, we might choose the logistic regression. And I didn't click on settings last time around the shade, but if you go into these algorithms, there are a fairly good amount of options and settings within them. I'd mentioned the ability to turn on and off binning and things like that. For logistic regression, we can identify the maximum number of model terms that we're even interested in. We have a model complexity penalty so that the Lityx IQ looks to build the best model with the fewest number of terms to prevent risk of things like multilinearity and such. This is where we can have those options around the binning and things like that. But none of this needs to be adjusted. It's all set with very strong defaults to build strong, robust models. And so in this tool, we would go ahead and, just as we did before, go ahead and execute this model, run it, and we can go ahead and look at this now, the logistic to performance analysis. And we go back over to our gains chart over here and see, we may or may not be able to detect a difference just eyeballing it. Not too much, you can't tell too much on here. So what we're going to want to do is look at these together. But we can, and we'll do that in a moment. We can go look at our model coefficients, similar, not so much the decision tree this time, but kind of more your standard coefficients with errors and significance. Now you'll see a lot of predictors listed here, but that's only because of the binning. If you go ahead and remove or sort of collapse the actual predictors by name, you'll have not more than what you had set the limit at, and most likely quite a bit less. They're generally listed in order, at least across the predictor. Perhaps there may be an element of a bin that is not as significant as another in there. We can go ahead and if we want to understand more about the binning within these, go ahead and look at, for instance, how the categories might have been together, or the numerics, what have you. So you can see that it's which values within this variable A00288 were being combined. So we can utilize some of the insights here. We'll go back to performance summary to really understand what's going on with the model. And let's go and look like we did before. And we'll just do lift and check all. I'll take that off. Go. And so if we recall from last time, 1 versus 2, we've got a bit higher lift here, 21%. 1 versus 10, quite a bit higher with the logistic. Now we're at like about a 4x increase, and over random, about a 72% lift over random. So the logistic definitely looks to be better than the shade. Now I ran both of those just on their own. I could have, as I had previously mentioned, run them together. So if I go into my model build settings, change nothing on the first screen, it will default actually to logistic regression as the sort of preferred algorithm for a binary type. But in this example, I ran them as shade and logistic. Now I could have, as I said, I could have gone and added a neural net to this, if I wanted to change anything there, and I could add a random forest, which is a sort of type of ensemble approach, and you could keep going, SVM, etc. And so you could go ahead and run all of these and compare them, do like your own sort of bake-off, which is really a nice option. And so we just ran the two, the shade and the logistics. So I'm just going to close out of this We'll go ahead and take a look at what those look like together. So if I go now again to my performance analysis, I'll go to my gains chart. Let's go over there. And this is all running off of Amazon Web Services. So this is all a secured connection to Amazon, all software as a service, cloud-based sort of technology. And so what we see here is we have iteration 1, the blue line, was the shade. And at least through the first 2 deciles, 20% of the file performs pretty much the same as the iteration 2 logistic. But the logistic really continues to maintain stronger separation deeper into the deciles. And so, what you would obviously do is you'd use the logistic over the shade. And, we could do some more model analysis. We could certainly continue to look at creating some further derived variables, do the types of things, ensure assumptions, whatever, you typically do to make you feel confident with the models. So what I want to show you, though, is how we might combine these two. And it may seem odd or even counterintuitive that the shade even has anything to offer to the logistic. That, hey, the shade, sorry, the other way around. That the no, shade has anything to offer. That the logistic even, could benefit from anything having to do with the shade. And sometimes it doesn't. Sometimes it does. So what I'm going to do now with these two is I'm going to go ahead and score up my original data set. I'm just going to put those predictive scores back on my data set. And so the way that in Lytyx IQ I do that is I have to execute a scoring job. And so I'll set up a scoring job, create a new scoring job, and I'll go ahead and do edit settings here since I've run one. And I'll just choose the model that I want to score. So I'm going to choose the response model and the data set that I want to score. So we're just going to score up that base model data. I set up a scoring catalog. So very simply just over underscoring catalogs, I created a catalog called models that the scores will go into. It's just a sort of a data table. And then I'm going to use the fixed boundaries from the model build. So I'm not going to, if by chance I was scoring a different file, I may want to have even, say, deciles on that other file. I'm just going to keep the sort of the cut points, the decile cut points. And in fact, I don't have to have deciles. I could have percentiles or ventiles, what have you. But I'm just going to have deciles. And so you go ahead and execute that. And run that job, and it also could be scheduled as with everything else. And I did the same for logistic, same routine, where I go ahead and point to the logistic model and score up that base model data. And so those two end up in the scoring catalog, and the catalog continues. I can have multiple catalogs, obviously, where I'm parking all my scores. So I might say, well, let me see the shade model scores. So here's the deciles and the raw score. So just to show you what it looks like. This is that sequence number that was on the base file, the unique identifier, and then the score for each record and the decile that they were put into. So this is like the data set that's sitting out in my scoring catalog after I've scored it up. So now I'll just simply go back to Data Manager and pen those scores to my raw data, to my base data, so that I can sort of, in essence, create a new data set for building my second stage model on. So if I built my initial models off of this, I want to have the actual response rate joined up with these predictions that I just did. And so I'm just going to do a simple join of those. And here you would do create new data set, and you choose a type view. And we're just going to edit that view so you can see. So we would choose add data set. And here, when I add the data set, I'm going to choose the base model. That's my main data set. And I'm only going to, out of all those elements in that data set, I'm only going to pick a couple of them. I just need the response, the actual response indicator, and then my unique identifier. And then I'm going to do a join with my scoring catalog called models. And I'm going to join on this sequence number, test n. And so that's the first tab of this. Once I've picked the two data sets, I say, what do I want to join on? So I just simply identify both of them. What variables do I want from each data set? Well, I definitely want all of those. And from my catalog, I might have other things out there I don't want. I'm going to bring over the logistic and shade deciles and scores along with my match key, my sequence number. And then I simply just tell it, keep all records from my left data set. So I'm just going to match it to that base one. And in this case, for clarity, I'm just going to create a sort of a new field from each of the scores. The system produces sort of a date timestamp value or field name for the score. That's a little bit busy when we go to look at it later. So I'm just going to call this logistics score and rename it. There are other manipulations I could do through various functions as well. I go ahead and execute that, and it produces this data set of 57,580 records, but now only 8 columns. And so if we can go ahead and browse that data, we'll see. So here's my unique identifier again. Here's my actual response. Here were the deciles for the logistic and the shade, and then the raw scores with kind of the long field name, and then the same scores, but now with the shorter field name, which we'll be using shortly. So all I did was create my initial couple models and then score up the data set I created the models on, and then join those scores up to that same data set with the actual value. And so now I have a new data set, slightly revised, that I can build my second stage model on. So I'm going to go back over to Predict IQ, and I'm going to build my ensemble model. And so it's still just a response model. So when I click Create New Model, I'll just build a response. Now, I could actually, if I wanted to, select any one of these and say, copy model, and just use if I had done anything special in it that I just wanted to tweak. So I'm going to highlight that one, and I'm going to show you with the. So this is actually kind of a point that maybe it's important to mention, of course, but maybe one of the questions is, how am I going to join these together? And certainly with the Netflix prize, they used a much more advanced approach to how they would combine. They had 500 different models that they were joining. In this case, we just have the two, and I'm going to point to this ensemble model data set, the one that we just looked at. Response, the actual response is still what I'm trying to predict. My predictors now just become the shade score and the logistics score. Those are my only predictors. But when I choose the algorithm, I'm going to do it in a logistic regression fashion. So, we use logistic regression as one of our, base or stage one models. I'm going to use that same approach then to combine my scores. I think it's a nice way, clean way to figure out the appropriate weighting across those scores. Now, intuitively, again, if you're not familiar, you may say, well, I can't believe that shade is going to have anything to offer to logistic. Logistic outperformed shade, so why would it even come in significant? So we'll see. So I'm going to use the logistic to combine them, and there's nothing else I need to, and even this I wouldn't have needed to fill out because logistic was the default. All right, so we execute that, and let's go take a look at the performance again, performance analysis. And so if we go to our, click on our performance details, and we'll look at, it's spinning up, getting the data. We get another gains chart. So again, you may not, through the eyeball, be able to see or just visually see that this is better. So we'll take a look in a moment. Had you kind of scrolled across this, we might have, see that with about 62% of the records I'm generating, 80% of the responses. I'm just kind of looking along here. If I go to my performance summary, and we'll go to lift. Let's go uncheck all and do lift. And so we'll check all the lifts, take that first one off. If we can remember last time, now we're up to 7.62. It was only around a 4x increase. So 1 versus 10 now is actually a 7.6 increase, and 1 over random is an index of 2.13, which would be a 113% increase. So much better lift there as we look across these. So what we can do as well is ask ourselves, well, how, if we go look at the model coefficients, how is it taking the 2 model scores? And so we just have the 2, but with the bins again, we can see that it ends up appearing as more 17. And so Logistic came in first, which is clearly what we would have expected, followed by the shade. And everything statistically significant here. Certainly some of these are contributing more value than others. And so we can start to do analysis now if we want more insight in this. Obviously, this model itself is good, ready to be used. If we wanted to use it, we could go ahead and there's an approval and implementation process. In order for a model to be scored, it has to be approved, and you can have external approvers and things. So we could go ahead and put this model in production. What I did is I went and scored up the original data set again so that we could do some further comparisons. So I'm going to go back over to Insight IQ and look at some comparisons. So when we do the shade only model, let's go ahead and view that. So this is the actual response rate by decile of that model. So we had sort of a 23% response rate going down to just a 5% response rate. So that's that rank ordering we saw by decile with the shade model. And this is, this would certainly still help a business considerably. If we go to the Logistic and shade side by side, and we view that, this is where we can see the Logistic is superior to the shade. So we go from a 27% in the top decile down to only 4% in the bottom, much stronger. And then if we want to look at the ensemble layered into this, this will help us understand that it is coming in better. So not a ton better than the shade, but you go from, let me get that out of the way, 28% in the top decile down to 3% in the bottom decile. And as we all know, small differences can generate big differences in profit or savings and things like that. So that's the approach. I think it's very straightforward. If it weren't for the fact that it was so simple, we might say, well, the hit and miss ratio, sometimes it hits, sometimes it doesn't, isn't worth it. But I think the process of examining multiple algorithms for one is beneficial. But then two, taking the simple approach to combining them is also, I think, can be quite beneficial as you've seen here. What I've done in the presentation as well is, if I go back over, I've put some resources out there. So I have a short article that I wrote on this topic that sort of walks you through this, called Ensemble Modeling, getting more out of your predictive modeling. And then there's some other articles I thought were nice, like a thumbnail history and some stuff on Netflix and Ensemble Modeling. With that, I can take questions, and I appreciate, we had 45 minutes scheduled for this, but I don't really want to take any more time than is necessary. If you would, please fill out your thoughts on this. The survey, there's a place where you can provide feedback, and I definitely appreciate you attending, and would love to hear from you if you have questions or just want to talk about this topic.